Welcome to the Food Chronicler. I am your host, Tommy Bleasdale. In this episode, I outline the genesis of cool season grasses. You eat their grains every day. They are the basic ingredients for some of the best foods on Earth. But first, the talk of global climate change rages. Change deniers and alarmists go toe-to-toe in our newsrooms, social media, and on our screens. Climate change policy is created, ignored, and destroyed in just a few years. It's all very well for humans, but how does a non-human species like grass wrestle with climate change? As it turns out, grasses already face climate change that we can only imagine, and arguably, we may not have been able to survive. Coming up next on the Food Chronicler, 35 million years ago, grass faced the Grand Kapir extinction when endless cold and ice swept across the planet. Winter was coming, and grass had to adapt or perish from the face of the earth. Living in the shade of giants. Then, the world began to change. Scientists tell us that 35 million years ago, the earth was warmer and wetter. Vast primeval forests spanned the continents, and a defining characteristic of that epoch, called the Eocene, is that the Earth's climate was stable. There was no polar ice like we have today. Winter, as we know it, was probably somewhat like the winter on equatorial islands such as Hawaii. Scientists credit the Eocene's warm climate to elevated levels of atmospheric carbon and methane. The world was experiencing a global greenhouse effect. Atmospheric CO2 for the year 2017 was about 405 parts per million. That was cause for alarm. It was the highest carbon dioxide levels the Earth has seen in almost a million years. But if we compare that to Eocene, it is estimated that atmospheric CO2 during that epoch measured about 2,000 parts per million. This was the perfect environment for forests. The plants use CO2 to photosynthesize light, so as the Eocene forests aged and died, they were buried and stored in the earth itself as coal, oil, tar, natural gas, peat bogs, and humic soils. Greenhouse gases were slowly stripped from the atmosphere, and by the end of the Eocene, the earth was about to change radically. In an event now known as the Grand Kapir, carbon dioxide levels fell so low that the greenhouse effect ended. Instead of a greenhouse effect, the world was entering what scientists now call an icehouse effect. In English, the Grand Kapir means the Great Cut, and it references the end of the Eocene and the beginning of the Oligocene. And with that, everything changed. Suddenly, the Antarctic, the fifth largest continent on Earth, began to ice over, crushing dense forests that had lived on it through the Eocene. To tell this story, I'm going to need a green screen. Plant and animal species which hadn't seen a frost or ice in the last 30 million years of the Eocene suddenly had winter. The great forests of the Eocene began to break apart as the Earth's surface cooled. Grass, which had lived in the shade of giant forests for millions of years, suddenly found itself with a new set of challenges. It was cold, very cold. There was a mass extinction. Many animals in Europe died out to be replaced with others from Asia, and there was extensive losses to both sea life and plant species. Ideally, grass could remain in a climate similar to the one that it had evolved in during the Eocene. That climate still existed. It is the warm belt around the equator. However, those areas are heavily jungled. The equatorial jungles are well adapted to resist grass's encroachment. They are considered some of the few places still today where grasses are almost entirely unsuccessful. Effectively, grass had been kicked out of its home environment. It had to learn to survive the oncoming winter or become another victim of the Grand Kapir extinction. But moving out into the cooler parts of the globe brought its own problems. In a nutshell, grass that is too cold can't photosynthesize light. This is why if you live in a place with cold winters, Most grasses will go dormant or die during the winter. There simply isn't enough heat for them to effectively photosynthesize sunlight. In many areas of the world, under the new ice house regime, there might only be a couple of months during a year when it reaches the magic temperature of 60 to 75 degrees. To step up the pressure even further, the ice house effect continued to intensify over time. The North Pole was ice-free until 3 million years ago. Then it, as the Antarctic had, iced over. Shortly after that, ice ages began. At their height, an ice age can cover some 40% of the Earth with glaciers. Sheets of ice reached out from the North Pole, freezing and crushing every living plant in their path. The weight of a glacier will grind rocks to dust. When glaciers retreat, they leave vast expanses of the continents completely bare. No soil, no seeds, just rock and lifeless clay. But grass did have a small advantage. During the Eocene, grasses could only thrive when there was a break in the forest canopy. Once there was an opening, grass would have just a few years, maybe a few decades at most, before trees would fill in the canopy and shade it out. To survive into the Oligocene epoch, grass would exploit this one tiny advantage it carried over from the Eocene. Every time the weather turned against grass, it also turned against the trees, killing some and forcing the others into dormancy. For grass, this opened up patches of land, giving it access to the precious sunlight. The gaps in the Eocene forest left by winter frosts and later retreating glaciers meant grass had one less competitor, a very significant competitor, and it could use its own opportunistic nature to move into the newly opened ground. Grass had another hidden advantage, one that evolutionary biologists are still trying to understand. During the Grand Coupre extinction, there was a sudden increase in the number of new species of grasses. Science can explain the why of grass's rapid diversification. Climate change had opened new regions of the continents as forests retreated. However, this does not tell us how the diversification process happens. What genetic mechanisms allow for the rapid surge in new grass species? A paper published in 2018 by Dr. Hodkinson states diversification of cool season grasses was especially intense during the Oligocene-Miocene, and the background diversification rate increased significantly at that time. And the biological and evolutionary reasons for these patterns of cool season grasses species and richness are not fully understood. What we do know is that grasses are open pollinated. This means that a single grass plant can gather pollen from all the grasses of the same species around it. While the resulting grass can be largely similar to that of the parent grasses, they still can vary widely in genetic traits. Wild grasses are essentially running a continual genetic experiment, testing what combinations are working and will allow them to thrive in a changing environment. Some cool season grasses have evolved biological mechanisms to avoid frost damage by controlling where ice itself can form in its own cells, or actually prevent ice formation entirely. The leaves of some cooled season grasses can survive temperature plunges to 10 degrees Fahrenheit or negative 13 Celsius, and those that can't will sleep out the winter underground until the spring wakes them up again. Cool season grasses are the foundation of some of the world's most memorable landscapes. Think of the steppelands of Russia, Mongolia, and Manchuria, the veldt of South Africa, the outback of Australia, the pampas of South America, the prairies and plains of North America. All these grasses live far away from the heated equator and in zones much, much cooler than they evolved in. But what makes this important to you? Well, do you like bread? I like bread. I love bread. I eat too much bread. The only reason I can eat too much bread is wheat is a cool season grass that evolved because of the Grand Coupre. How about beer? I'm a fan of beer. Beer is essentially fermented wheat. How about whiskey? It's made of barley, rye, and wheat. Barley and rye are, you guessed it, cool season grasses that evolved because of the Grand Coupre. And then there is rice. Oh my goodness, sticky rice rolled up with some raw fish and seaweed, sushi, or aromatic rice is the foundation of a curry, or Cajun dirty rice. Oats, that's another good one, a cool season grass. How nice is the cereal aisle of your grocery store? Take oats, wheat, and rice away and you cut that cereal aisle down by more than half. Human existence today relies upon cool season grasses that survived the jungles of the Eocene and adapted to the transition from a global greenhouse to a global ice house. But the challenges the grass would have to survive so that the human story could unfold still were not over. Next time on the Food Chronicler. The onset of the Oligocene age plunged the world into endless cycles of winter and ice. Cool season grasses had managed to survive global cooling and glacial maximums, but expanding polar caps and glaciers meant that the Earth's fresh water was being locked up in that same ice. Precious little water was left in the atmosphere for rain. Entire regions of the Earth started drying out, and deserts formed. Forests simply crumbled in the new arid regions of the globe, and grass would have to act fast to find a way to survive the rapidly expanding deserts of the world. If you have questions or comments, post them below. I'll be filming a segment about the science behind this episode next week, and I'll respond to you in that video. If you like this story, subscribe to follow it. Thank you for watching. 3 reps. That's good enough for the week.